Section 2.3 introduces us to the limit laws. Some of the limit laws are probably a little obvious. I'm going to focus on product law. The limit of a product is the product of the limits. And one that I'm going to use today is the quotient law. The limit of a quotient is the quotient of the limits. So I leave these to you to remember. Let's look at an example. I have the limit as x approaches -2 on this expression, and your first thought should be to substitute -2 in wherever there's an x. So if I do that, I'm going to get -2 squared minus 3 times -2 minus 10 over -2 squared plus 5 times -2 plus 6. You end up getting a 0 on the top and you get a 0 on the bottom. Now what we've done in the past is we've allowed you to write 0 over 0, indicating you're getting 0 when you go straight forward evaluating this limit. In fact, we don't want you to write that ever again. Instead, the appropriate way to approach it is to change this into a quotient of the limits. So on your paper, you need to write the limit as x approaches -2 of x squared minus 3x minus 10 for the numerator. And then for the denominator, you need the limit as x approaches -2 of x squared plus 5x plus 6. And you evaluate these limits independent of each other. So when you do substitute in -2, you'll get 0 in both instances. So this is how you should be showing your work when you first approach this problem. Now that you realize there's an issue, we'll attempt to do some algebra. So the first thing I'll try is factoring. Factoring does work. The numerator factors into x minus 5 times x plus 2, the denominator into x plus 3 times x plus 2. Now we're allowed to cancel the x plus 2 factor, and we can evaluate the limit now. Substituting in -2, I get -7 in the numerator, and I get +1 in the denominator. So in fact, this limit is -7. That tells us why we cannot write the original limit equals 0 over 0, because the original limit does not equal 0 over 0, it equals -7. So it is incorrect to state 0 over 0 for this limit. Therefore, you would get marked wrong for that on the AP test. Another type of question you may come upon is the next example. If you approach the next example with the first strategy, that is to substitute 0 in, I want you to take the numerator and write the limit as x approaches 0 of the square root of x squared plus 4 minus 2 is the square root of 0 squared plus 4 minus 2, which is 2 minus 2, or 0. So you could do that. And then take the denominator. The limit as x approaches 0 of x squared is 0 squared, which is 0. So there's valid writing that you could do. But again, in this case, we're getting 0 over 0. So we need to do something. We can do algebra. So what I'm going to do is I'm going to multiply the top and bottom of the fraction by the conjugate. So I'm going to write the problem out again. And the conjugate of the numerator is the square root of x squared plus 4 plus 2. And now I'll multiply. So in the numerator, when I multiply, I'm multiplying conjugates. So that means I just really need to multiply the first together and the last together. So in the numerator, I get x squared plus 4 and minus 4. This becomes the limit of x squared over x squared times this quantity. So the x squareds are going to cancel, And now I can evaluate the limit. Here again, the limit actually comes out to a number. So if you start out by telling us the limit initially equals 0 over 0, you would be incorrect in saying that. So do not get in the habit of writing 0 over 0. The next theorem I'm going to talk about is the squeeze theorem. If your teacher has you learning this, I'm going to include it. The math problem starts with three functions, f, g, and h. So if we look at the hypothesis, if f is less than or equal to g is less than or equal to h, I'm going to draw a picture of what that might look like. So that means on a graph, h is up above f and g. So this will be our h. Here's an f, and it said the limit on f as x approaches a equals the limit on h as x approaches a. So that means they have the same height at a. If they have the same limit at x equals a, and g is in between them, that means g also has that same limit at a. So g in between them might look something like this. The idea is, if you're familiar with function f and you're familiar with function h, but you're not familiar with function g, you can use f and h to zone in on a limit for g at that point. So that's the idea in the example. Show that the limit as x approaches 0 on x squared sine of 1 over x equals 0. So what I want to do is start with something I know. I know this part of it right here, sine of 1 over x. That's the sine function. The sine function has a range of -1 to +1. So the output of that function is going to be somewhere in between -1 and +1 inclusive. My issue, however, is the entire x squared times that. So I'm simply going to manipulate this inequality and multiply all sides by x squared. The new inequality looks like this. So these are the players. Negative x squared is like the f function we're supposedly familiar with. X squared is like the h function, whom we are also familiar with. But the g function in the middle is the unfamiliar one to us. Now this limit headed to 0. So this was as x approached 0. So take a look at the first function. Let's find the limit as x approaches 0 on negative x squared. Well, negative x squared is simply the parabola opening down whose vertex is at the origin. So as we approach 0, this limit approaches 0. Also, we know about x squared. The limit as x approaches 0 on x squared is also 0, because if you remember, the x squared function is a parabola opening up whose vertex is at the origin. So as you approach from the right, or as you approach from the left, you'll attain a limit of 0. So therefore, by the squeeze theorem, the limit as x approaches 0 of x squared sine x of 1 over x equals 0.